So today's class will be mostly the discussion pending on nuclear overhauser effect and its application. Okay. In the last class, we tried to understand how the enhancement occurs by nuclear overhauser effect. We were discussing the saturation points, okay, and then we tried to, we were left out with the relaxation, okay, routes, if you can recall from our last class. So what we have seen that when you irradiate separately the one atom, okay, one nuclei, say suppose in this case X nuclei, to make it saturated. So your population of the nuclei at the ground state alpha and the beta, when they are same, we call that state as the saturation state for that particular type of nuclei. Okay. Now, in this particular figure, what we see is that for X, the beta population is 4 and the alpha population is also 4. So here the populations are same. So there is no excess population at the ground state. Okay. And we call that this particular nuclei, since you have the alpha and beta state are equally populated, this nuclei will be NMR inactive at this situation. Okay. Now, if we look at nuclei A, you have the population at the alpha state is higher than the beta. Okay, so you have alpha state is having excess population of 4. So this excess population will help you to have the NMR. Okay, but remember what I told is when your excited state for the X is getting overpopulated, then the normal Boltzmann distribution equilibrium, what we have discussed earlier is that your cross polarization will happen, and that will allow the nuclei to relax to a new equilibrium state. After achieving the new equilibrium state, what will be the situation of the excess nuclei at the ground state? Based on that, your NMR signal will come. So let us look at that relaxation route. Okay. So in this case, you have I have considered the single quantum relaxation, okay, via omega 1 route. So before relaxation, what we had, the signal of A nuclei, you have excess population 4. So the intensity I took as 4, and for X there is no peak. Now let us consider the relaxation by single quantum route. Now single quantum route, when you talk about, we are doing the relaxation of beta beta state to beta alpha state. Okay. So that means you are having beta beta state to beta alpha state. Okay, so we are considering beta beta to beta alpha state. So this route, okay. Now if you do that, what we will have? We will have, say suppose you have one of these nuclei is jumping here, okay. So what will be the situation? This is the beta beta, from beta beta to beta alpha route, okay. What will be the situation here? You have x having excess, x having population at the beta state will be 3, whereas the alpha state will have now 5. So what will be the excess nuclei for x? It is 2, right? So 5 minus 3 is 2, whereas at that route you don't have any change to the excess nuclei corresponding to the A, so it is remaining the same. So this is, I am considering only one omega root, okay, the single quantum transition or relaxation. Got it? So in this case, what we will see is you don't have any change in the peak intensity of the A nuclei, okay. In our case, it is 13C, okay. Whereas we will see a tiny peak will appear for X or the proton nuclei, okay, if you do this route transition. Got it? Now let us consider the another route. Now 2 quantum relaxation via omega 2 route. Now your saturation was again the same. You have excess nuclei for A is 4 and that of X is 0, okay. As usual, you have the signal due to A was 4 and you have the X was in saturation, so you have no signaling here, okay. Now we are doing the relaxation via omega 2 route. So what will happen? You will have beta beta to alpha alpha state decaying. So you have beta beta route, okay, beta beta state. From here you are having alpha alpha state. Getting? Now if you do that one, what we have to consider, from beta for A it is beta to alpha transition, and for B it is beta to alpha transition 2, okay. Now we have to do in that way in this distribution. So what we have to do is, this is the beta for X, so I have to change one from here to here, okay. This is the relaxation for beta to alpha in the case of X nuclei. We have to consider the beta to alpha of A nuclei too, okay. So we are considering beta to alpha of A nuclei. What will happen here? For X you have 3 population at the beta state now after relaxation and 5 population at the alpha state. So you have the excess population is 2, whereas for A you have beta state having 1 population and alpha state you have now 1 2 3 4 5 6 7. So you have 7 population, right? So your excess nuclei is 6. What will be the situation for the signaling? Signaling will be 6 for A and 2 for X. Now what you have observed here is that when you are allowing the beta beta to alpha alpha transition, your number 4 or the intensity, it has increased to 6 for the second, I mean the 13C or the A nuclei, Okay, so the intensity has increased. Intensity has increased. Okay, so what we can see, like in 2 quantum relaxation after saturation point, okay, you have an excess nuclei is more than at the saturation point, and that will help the enhancement in the peak height. Okay, so that we observe for 2 quantum relaxation route. Let us come to the 0 quantum relaxation. Okay, 0 quantum relaxation, what does it mean? You have to come from alpha beta to beta alpha. Okay, same situation, we will be considering the transition or the relaxation from the saturation. Okay, so this is the saturation state. Now you have alpha beta to beta alpha transition. Okay, so alpha beta to beta alpha transition. Now in this case, what you are seeing is, for X nuclei, your beta to alpha relaxation is happening, whereas for A nuclei, you have alpha to beta transition. Okay, so for X, you will have beta to alpha transition. Okay, the route of relaxation, and for A nuclei, you have alpha to beta, so you have the opposite transition. Okay, so that you have to consider. If you do that, what will be the situation? You have, for X at beta, the population is 3, and in the ground state it is 5. Okay, so excess population now 2. For A, you have excess population will be 2 again. How? You have now, after relaxation, the population at B is 3, where population at beta is 3 and population at alpha is 5. Okay, so you have excess population 2 again. Now what we'll see in the spectrum, what changes you will see in the spectrum, that will be, you have the A nuclei, you will see the decrease in peak height. Okay, the intensity. So it is, you look at from the saturation, you have initially 4 was the excess population, now it became 2, and that's why your A nuclei peak height is decreasing. Okay, you have the nearby peak due to X nuclei, but we can easily understand, if you allow one nuclei to undergo saturation and then you allow for relaxation with suitable route, you can have the peak height enhancement or the decrease in peak height for the nearby nuclei, which is staying close proximity of the nuclei which you are making to undergo saturation. Okay, so this part is clear to you now? Is it clear?
Yes, sir.
So you can explain, right? If it is coming in exam, you can explain why the peak height will be increasing in certain cases, why it will be decreasing. Okay, at what quantum transition what will happen, right?
Yes, sir.
Now the thing is, for 13C and proton system, we find that the relaxation route is the 2 quantum route. Okay, the omega 2 route. Omega 2 route is observed for 13C and proton interactions. Okay, so 13C and proton system, you will have relaxation route is omega 2. That is the most uh, decaying route we see when it is undergoing the relaxation to achieve a new equilibrium state for 13C proton system. We do find the relaxation route is the omega 2, because in this case we always find the enhancement, and that is the well known I mean, it is well experimented. Okay, but it is not true always for any nuclei. So there are certain nuclei, instead of enhancement, we do see the peak height decreasing, the intensity is decreasing. Okay, contraction of the peak height. So now we'll try to apply some of these, I mean, this nuclear Overhauser effect to certain molecules. Okay. Now remember, when I'm telling the two different nuclei, it doesn't mean always it has to be 13C and proton. Okay. So in any organic molecule, you can apply this one even for proton and proton. Okay. If the two protons are closer enough, one proton have the nuclear Overhauser effect to the another proton. So you can have the cross polarization due to one proton saturation to the other proton. Okay. Now, if you remember the nuclear Overhauser effect or enhancement, NOE, that if you remember that enhancement equation, what was the equation? Can anybody tell?
Delta plus twice X.
Enhancement. Okay.
Observe.
Yeah. So observe. Okay. Understood. So it was the enhancement. Now, if it is the two proton, what will be? Suppose you are particularly one proton you are considering, and that proton, whatever is the peak position, based on that you are selecting the selective irradiation wavelength. Okay, the frequency. Understood. So that will help that proton to undergo quickly saturation, and it will have the impact to the nearby proton of that proton environment. Okay, so in this case, what you will expect the nuclear Overhauser enhancement maximum, how much you can get. So this is half, right? Because both the proton, your gyromagnetic ratio or magnetogyric ratio is the same. This for proton it is 267.5, right? So that will be cancelled out for proton 1H. So it will remain only half. That means you have 50%. Okay, understood. So your enhancement for proton-proton nuclear Overhauser experiment will be 50% maximum. Got it? Whereas for 13C, it will be 200%. Okay, so in the last class, so 267. Okay, for 13C to 267 by how much it was bottom? Can you remember for 13C gyromagnetic ratio? Anybody?
Sir, 67.28.
67.8. Okay, so that means what you will see is this was, we have seen this around 4. Okay, so half into 4 by is equal to 2, so it will be 200% into 100%. Okay, so 200%. So this is half into 100%. So it will be 50%. So proton-proton nuclear overhauser effect experiment will give the peak enhancement of around 50% maximum, and for 13C it can go maximum 200%. Okay. Now let us come to some problems. Okay. Suppose you have two identical molecule, I mean two isomers. One is cis, another is trans, right? Or EZ you can tell. So this one, what we'll call? This is E or Z? This one, what we'll call? This is E or Z? Can tell? Which
Z.
one is?
Z, sir, Z.
The compound 1, will it be E or Z?
So Z.
Compound 1 is Z, and compound 2 is E. So you have 3 carbon attachment here. You have 2 carbon attachment here. Sorry, you have carbon and nitrogen attachment. Here you have carbon, carbon, carbon attachment. So if you have another, so you are telling this is Z, this is E. Okay, what you will understand, I mean, how you will differentiate these two isomer by a nuclear Overhauser experiment. Can anybody tell? So you have two nuclei, I mean two molecule. Okay, it can be in Z or E form. So how to understand which form? Suppose you have one form is present in your sample. Okay, so how to confirm that one through NOE experiment? So what you have to do? Can anybody tell what you have to do actually? So you have to do, to find out, okay, you have to find out a suitable proton environment which are varying, okay, with respect to two isomers. You got my point? So you have to find out one proton in the molecule. That proton environment is changing when you are changing the isomer. Okay. So in one environment, that proton will have different protons which are very close. In another environment, the same protons are far away. Okay. You have to first identify that proton, and then you can, what you can do, you can selectively irradiate that proton to find out nuclear Overhauser enhancement, so NOE, right? So now you tell me compound 1 and compound 2, in this case, which proton you can consider to have different environment? and different environment with in its close proximity. Okay. So can anybody track that proton? So if I give the number, okay, you have 1, 2, 3, 4, 5, 6. Okay. So these are the different number I have given. This one you can take as 4 prime and this is 3 prime. Okay, these two protons, different protons. You can take 4 prime, 3 prime, and the same for here also. The same numbering you consider here also. Now you tell which proton you can have different environment.
5 protons, sir.
5 proton and
6.
no, what I'm telling is if we just take 5 and 6, so 5 and 6 they are having the same environment, right? They are having the same, if you just consider that 2 protons. Okay, because you cannot find any change between these two. What I'm telling is you have to track one proton. Okay, with respect to that proton, you have to consider another proton which are changing their proximity. Okay, in NOE, what you have seen is NOE you have with distance, so it is proportional to see, right? So your space distance, spatial distance, that depends. Okay, so if your distance is more, your NOE will be less. Distance are close, I mean shorter, so you will have more NOE. Now, if you look at this 6 proton and 5 proton for compound 1 and compound 2, both are of same distance. So you cannot consider that 2 proton, okay, for NOE experiment. So you have to consider a specific proton which you can irradiate to find out the impact. Can anybody tell?
3 days and 4 days.
1 and 6. 1 and 5.
Yes, so that is correct. 1 proton and 6 proton. If you look at this is 1 proton and 6 proton. Okay, getting
Yes, sir.
differences. So this is 1 and 6. This is 1 and 6. Okay, so that two they are changing the proximity. They are changing, right? So that means you can take proton 1, irradiate it, and to observe the change of proton 6. Okay, so what you will see for compound 1, if you irradiate proton 1, what will be the situation for proton 6? Will it increase? I mean, where do you see the NOE is more? Compound 1, compound 2. If you consider the 1 and 6,
Sir,
1 will have NOE more, right? 1 will have NOE more.
yes.
So that's why you see here I have given
Distance is less.
you look at here. So for this proton and this CH3 proton, they are now closer, and that two are away from each other. So when you are they are much away from each other, you will have enhancement is very poor, or sometimes you may not see any enhancement. Okay, in this case experiment tells it is near about 0. We cannot see any peak height changing that much, or it's negligible. Okay, whereas the situation is completely different for compound 1. Compound 1, you see the enhancement is 31%. Okay, so that means if you these two isomer if it is given to you, I mean one isomer is given to you, and if it is asked, find out this is which isomer by NOE experiment. So what you have to do first? You have to do first run the proton NMR. Okay, so from proton NMR you assign the peak, which peak is for which one. Okay, and you come to the peak respectively, I mean the peak due to this proton, okay, and peak due to this proton. So that two proton you assign first. Okay, now you do the NOE experiment. So what you do? You do a special experiment, just irradiate properly the peak position where you are getting for this proton, okay, selectively, and see the NMR again. Okay, what you will see, if this is your compound, you will definitely see the peak position due to this CH3, okay, that will increase, okay, before the what you had before NOE experiment. So this is clear to you?
Yes, sir.
So who has any problem to understand this one? Anybody is there? So this is one option. Another option is you can consider proton 1 and proton 5 too. Okay, proton 1 and proton 5. Okay, so 1 and 5, if you this was 5, you look at this is 5. Okay, 1 and 5. So that in compound 1, that 5 proton is away, right? And
Yes,
compound 2, 5 proton is closer. Okay, so if you irradiate the proton 1, for compound 1, there will be no enhancement in the peak of proton 5. But in compound 2, you will have the enhancement because you have these two proton there closer. Okay, understood?
yes, sir.
So that can be another option. Okay, so when we will do the NOE experiment, you have to do the experiment and see where the changes are happening. Okay, based on that, you can assign the position of the proton properly. Okay, now second molecule I gave here. So identify the proton, which one you can consider to find out these two different conformer. Can anybody tell which proton you will look into?
OCS3 XL
Okay.
and equatorial position.
So you have, I'm giving the all protons position so you can understand. So this is 2, here I'm giving 3, okay, this is 4, and these two are identical. So these 2 methyl, okay, I'm writing this is 4 dash, okay, and this methyl proton I'm giving 5, okay, this is I'm putting as 2 dash. So now tell me which proton you will consider to do the NOE experiment.
5
proton and so this is 5,
4.
this is 1. It is always better to consider the closest proton. Okay, if you go away, much away,
105.
if you go much away, your interaction will be decaying, okay, less. So if you consider 4 and 5, you see the distance here, it is far away. So you will not see any impact. Okay. If you look
1
at here
and
also,
5, sir.
if you look here also, that also far away because this is connected with oxygen. So you have one more bond has increased. So that
Oh.
may not be very close to this one. Okay. So which one do you prefer?
1 and 5, sir.
1 and 5 we cannot. 1 and 5 they are the same proximity. I mean they are the, you don't have any change here, right? This is 1 and 5. The distance here and distance here will be the same. Yes or no? This is equatorial and axial position for both the cases. So you know any change here. So which one do you think? So which two proton you can consider? Nobody?
2.
Yes,
5
sir.
and 2.
5 and 2 again is far away. Okay, look at the distance. As much you are making the distance, okay, covering the distance, if the distance is going away, you will not
2
see
dash.
impact. Okay, you will not see impact. 2 dash.
Four and 2. Sir, 4 and 2. 2 dash.
So your see the position 2, it is fixed for both the compound, okay, and position 4 is fixed for both the compound. So you will have, there is no impact you will see. I mean that will be same. Whatever impact will be for both the compound will be same. Okay. Are you getting what I'm telling?
Yes, sir.
Yes, sir.
So what are the two? Look at. Are you getting? So 4 and 1. Okay. 4 and 1. This was 4. This was 1. So 4 and 1. So here 4 and 1 are two axial 1-3 position. Here 1-3 position, one is axial, another is equatorial, far away. They are closer. Okay. So if you irradiate 1, you will see enhancement for compound 1 for proton 4. Okay. Whereas for compound 2 there will be no enhancement. And that we see the enhancement here is 12%. Okay, it's experimented. So you have to properly find out the protons. You have to do the NOE, you have to find out the proton properly. Okay, so that is the thing here most important. Let me give you another. Okay, you try this one. These are the two isomer, stereoisomer. So try to quickly find out. So see the position of oxygen here, this position. So here this is position. So what we see is the change here. So here is the change. Okay, your double bond was here, was this side, or was this side, it came this side. So which two proton you have to consider now? So you have, I'll give the hint here. You have 1, 2, 3, 1, 2, 3. Okay. So which are the two protons you have to consider? Out of 3 is very easy now.
1 and 3.
1 and 3, right? This one is, sorry, this is I did wrong. This is 3, this was 2. So if you look at this proton and this proton, they are closer. When you are having these 2 isomer, they are going far away. Okay, so your NOE for these 2 is almost 0, whereas for compound 1, the proton 1 and proton 3, you have enhancement of 26%. Okay, so this is this way you have to identify the proton and apply to find out the different isomer. Okay, look at this one. So you have 2 isomer here. What we have the difference is the substituents. So in this case, the substituents you have so your 3 methyl are here, your 3 methyls are here. Okay, so how to identify which one is what? So where you will have the enhancement, and that is due to which type of proton you have to consider. So you have proton here. Okay, so I'll give the, you have proton here, proton here, so you have proton here. Okay, you have methyl proton. So let me give the number. This is 1, suppose I'm taking, this is 2, this is 3, 4, 5, 6. Okay, in this case I'm just putting don't have here, I have to take 1 proton. This is methyl. Okay, this is, you have 1 proton. So this is, if I take 1, 2, so here 3 has changed. So here is 3, here is 3. So if I take, this is 3, this will, I have to take 6, 4 and 5. Okay, so what will be the situation? Which 2 group I have to consider? Which 2 proton I can consider to look at the differences?
One and 3.
1 and 6, sir. First.
Yes, 1 and 6 will be the most prominent one. Okay, 1 and 6 will be the most prominent one. If you look at the assignment, like this 1 and 6, okay, they have 33%. Okay, 33%. Whereas if you have the methyl here, okay, the 6 methyl for compound 2, if you look at, they are close also, but that is giving the impact of 11%. Okay, so what you will see, if you consider 1 and 6, you will have more enhancement for compound 1 and relatively less enhancement for compound 2. Okay, and if you have 2 different spectrum, you can easily identify which one is for which one. Okay, I don't have the data for this position 2 proton, 2 and this 3 interaction. Okay, that 2 can be considered also, but you will have more distance between the 2 and 3. Okay, if you look at 2 and 3, that distance will be more than 1 and 6 proton. Okay, that will be a bit more closer. So your proton will be like this. So that will be more closer. Okay, so 1, 6 will be more suitable interaction. Okay, got it. You have one more example like this two, okay, where you see the proton here and the proton here. Okay, now you can easily understand these two proton, they are closer, and these two will be away from each other. So if you can choose this particular peak position and irradiate it, if you are looking, the methyl proton is enhancing, okay, the NOE is enhanced, you can see the enhancement in the peak intensity, then it will be compound 1. If you don't see any peak intensity, it will be compound 2, okay, that we have shown here, okay. So you'll have large NOE here, you will not have any NOE. Got it? Now one more application, one more way to do the NOE is the two-dimensional.
Yes, one again.
Huh? Anything?
So previous one that
Tell.
in the slide, the 1 and 2.
Yes, yes. Tell what is.
Again, so, my connection was lost, so I can't hear anything.
Okay. So the first, the previous one, what you see is the position 1, okay, compound 1, the peak position 1 proton and 6 proton, they are closer, okay, are you getting? They are closer. And for compound 2, the 1 and 6, they are far away, right? Are you getting? So
Yes.
that means if you irradiate 1, the 6,
Yes, sir.
6 methyl, okay, this proton, you will see enhancement. So that is, you are seeing here 33% enhancement, okay, you will have more enhancement. But you will not see enhancement of the proton is methyl if it is here. If you selectively irradiate this proton, you will not see the enhancement of the methyl if it is here, okay. So you will not see any enhancement in this case, okay. But if you take the proton 2, okay, 2 and 6 if you consider, so 2, 6 for compound 2, you will have certain enhancement, okay, and that is 11%. Are you getting? So it is 11%
Okay.
for
Sir,
compound 2, but compound 1, 2 and 6 you will not have any enhancement, okay. So this way you can differentiate,
Yes, sir.
okay.
Thank
But 2 and 3 you will not see that much changes because that two protons are of same distance, okay. Here for compound 1 and compound 2, that will be of same distance, so you will not see any enhancement. Got it? So I'll quickly take another 2-3 minutes to finish the most important, one of the most important part of NOE. It is the two-dimensional NOE experiment, which we call it as the NOESY spectra. Okay, so this NOESY, Nuclear Overhauser Effect spectroscopy. Okay, NOESY spectra we generally consider for 2D, two-dimensional NMR spectrum. What does it mean by 2D? I'm not going to the detailed experiment. It is it's more technical part. But what is more important for us to know how to interpret the molecule from the spectra. So how the spectra will look like? Okay, what is the salient features? So in 2D NMR, okay, of NOESY, the proton NMR of the compound placed on X and Y axis. So you have X and Y axis. Along the X axis, you have to put the proton NMR of the compound, and Y axis also you have to put the proton NMR of the compound. Now, what you have to do, there will be two types of spots in the experiment. What we see, two types of spots we find. We have diagonal spot and we have off diagonal spot. Diagonal spot means along the diagonal, okay, and off diagonal is not at the diagonal, okay, outside the diagonal. Okay, we'll have the spots generation of the compounds. Okay, diagonal spots are due to the same proton from the both axes. Okay, since you are placing the proton NMR in X axis and Y axis, so you have suppose one proton, proton X, okay, of a particular compound, along the x-axis and the same compound along the y-axis, the same proton, they will be contributing the spot along the diagonal axis, okay, diagonal of the spectrum, okay, and off diagonal spot will appear for the protons which interact through space with shortest distance, okay. If you find the two protons, they are closer enough, okay, that two proton will contribute the off diagonal spot. Did you get this point? Okay, it will more clear if I give the with example, if I explain. So let us consider the this compound, okay. This compound, if you look at the NH proton and methyl proton, okay, NH proton and methyl proton, they are closer in this form, okay. Let me give the proton NMR of the compound. So this is the proton NMR of the compound. This 9.8 peak is due to the NH proton, okay. So this is NH. That you should be able to analyze the spectrum, but there is no time, so I'm just telling which one is for what. So NH proton will be 9.8, 9.8, 7.5. 7.5 will be the proton which is this one, these two, okay. These two proton will be 7.5. The middle one is the middle one, okay. These meta protons is the middle one, so that means 7.3, and 7.1 will be this proton, okay. So this proton will be 7.1, and methyl, of course, it is nearby 2, okay. So 2.06. So this is the proton NMR. Now the NOESY spectra, two-dimensional, will be looking like that, where the proton NMR we are placing at the x-axis and y-axis. So how we are placing? 0 to 10, okay. So in this direction, 0 to 10. Here we are placing in this direction, 0 to 10, okay. Now if you do that one, we see the diagonal spot, means this is the diagonal spot. So these spots are diagonal. Are you getting the spots diagonal spot? Yes or no? Quickly.
Yes, sir.
So off diagonal spot means this is off diagonal spot, okay. These two spots are off diagonal spot. Now diagonal spot, let me explain what is diagonal spot. If I consider the proton, okay, this proton around 7, okay, and here also around 7. So that two from both the spectrum, if I extend where they will meet, that will contribute the that will contribute the diagonal spot due to that particular proton. Similarly, if I consider the middle one around 7.3, so I have to consider from here and here. If you look at, so this one and this one, they are considered the same proton from both the axes. So we are having a spot. Similarly, you have 7.5, okay. So they are having the same spot. Now look at the NH. So here NH proton, right? This is NH proton around 10. This is also NH, okay, around 10. So this NH and this NH, so they are coming. So I have to consider this one and this one, okay. So this is again diagonal spot. This is again diagonal spot due to NH from both sides, and this is again diagonal spot due to methyl from both sides, okay. So ultimately you have, these are the diagonal spot, right? So this diagonal spot. Now off diagonal spot, these two spots are off diagonal. So NH and methyl. Now if you look at NH and methyl, they are not connected, but they are closer enough, right? They are closer enough. So what we see is this NH and methyl, they are having NOE interaction, okay. They have the effect on nuclear overhauser, okay, NOE interaction. So what we will see here, the methyl here, okay, from Y you have a methyl around 2, okay, Y methyl 2, and X NH, okay, around 9.8. So that two will be interacting to give the spot. So we have a common spot development here. And similarly, you can have another spot if you take the NH from y-axis and methyl from x-axis. So that peak is the off diagonal spot. So interaction between NH and methyl. So that two spot will be generated. Okay. So this off diagonal spot is due to the NOE experiment, two-dimensional NOE experiment. Is it clear now?
Yes, sir. For 7.5, who is proton?
7.5 is this is the closest one, the more electron withdrawing one. So you have amide, so you have this orthoproton. Okay, this is 7.5, 7.5. These two, 7.5.
Okay, sir.
Then you have 7.3, then 7.1. Okay, got it. And this NH is around 9.8 and methyl is 2. So this is it clear?
Yes, sir.
So I'll give some question on this NOESY. You have to solve. Okay. Maybe I'll give in the group. Okay. So you have to solve it. Next day we'll discuss those problems. Okay. So I'm not giving right now here. So I'll post it. Okay. The problems. So you will try to solve that one. Okay, so we are closing here. You have another class, so I'm just stopping here. Okay.